Hello, my name is Tavasszy. I'm a professor in freight and logistics systems at Delft University of Technology. In this presentation, I'm going to introduce the results of one of our master thesis students, René Siepman, about uncertainties in carbon footprint measurements. The work was part of an internship at Districon, a Dutch consultant. You can find the names of her supervisors on the slide. Our presentation will inform you about why these uncertainties are important, what are the possible causes of uncertainties, and how they propagate into carbon footprint indicators. I will first give a brief background to the problem. As you all know, it has become obligatory for companies to report their carbon emissions. As they cannot be measured directly, they have to be calculated from data about the transport activities of companies and approximated using indicators for energy consumption and emissions per unit of activity. It is here where the risk of mistakes creep in. Although we would like to make this approximation as accurate as possible, data is often non-existent or of very poor quality. More importantly, perhaps, there are various detailed ways to make calculations and many underlying assumptions that can be made. For this reason, standards have been in the making for quite some time now. As these have to be used in many different circumstances, they need to be specified at a very general level so that they are broadly applicable. This, of course, goes at the cost of accuracy. As industry parties like things simple, communities have been quick to agree on straightforward methods that are easy to implement. As a natural consequence of this, the use of standards for approximating true emissions is fraught with uncertainty. This can be problematic if the uncertainty is very high and we do not know how to deal with it. This figure on the right illustrates a simple example of differences in emission factors between world regions. One might argue that if the scientific basis for these differences is weak, they result in unwanted bias with unwanted economic consequences. The table here before you gives a brief snapshot of a couple of years ago of the different standards and tools that we're developing. While the standards are clearly building upon one another, as the standards have been evolving from EN to GLAC to the current ISO standard, which was just introduced, and one can say that there's a certain degree of evolution here, it is not clear whether the tools do the same. The next slide shows a nice example of the complexity of emission calculations in the logistics context, which can create uncertainty in final indicators and also confusion. You see two situations, one with a very simple trip from one supplier to one receiver, and one with a round trip from one supplier to multiple receivers, where the vehicle is shared for different shipments. The second case introduces the problem of how to allocate the different emissions to the different shipments or even to the different destinations. We have to know how the shipments are distributed over the destinations, and we have to know how the different distances are from destination to destination. If this information is not available, we have to make guesses. So allocation factors like this, they can be difficult to establish. There are many different rules for this also, as it has to be fair and also efficient. But without knowing that, we are left to some simple approximations. Now, the objective of the study here, with this problem in mind, was to create a framing for uncertainties in this context and develop a tool that can support the identification and the interpretation of uncertainties in carbon footprint measurement. René Siepman developed an Excel tool also that I will not introduce here, and my focus will be on the storyline of the uncertainties themselves. So, from a deep dive, framing these uncertainties, look at how important they are and how we can assess their complexity, to determination of methods to quantify these uncertainties and to create approaches to identify and to deal with these uncertainties. We distinguish between three major causes of uncertainty. One is variability, which is created by inherent randomness in our representation of reality as a necessary consequence of aggregation of activities or technologies or time. So when we want to portray something over a whole year, and if we have data of different years, then calculating an average is not straightforward, and the variation around it should be known. Second is about ambiguity. If people mean different things when they use the same words, such as carbon or footprint or truck or diesel, then we have a problem because it will be implemented differently. Third possibility is epistemic uncertainty, where we lack knowledge about certain processes or activities. Now, these phenomena can be applied to different aspects of the problem, including the context itself, so the boundaries of the system, the model structure that we use, so the actual decarbonization formula, the input data that we have, whether they're accurate or not, the parameters inside that would be unknown and would need to be estimated or would to be represented by other processes. And finally, the actual software or hardware faults, the errors and algorithms and so on, which we call the model technical sphere of uncertainties. So mapping these for the carbon footprinting process was an interesting but rather daunting task, and it's not easy to summarize. So I have a slide which gives you a peek into the unrefined results, so to say, of this entire process, and this is it. I mean, I don't mean to show the details or explain the details here. You can see the setup where the context is on one column and the other column is about the different types of uncertainty, and in between you see descriptions of all these phenomena. The detail is available in the report that can be downloaded. There's a URL on the first page for this, but I will show a summary of the most interesting points, some salient points in the next slide. And I hope you agree that such a little encyclopedia of uncertainties is useful as a starting point to take more detailed and substantive steps to manage uncertainty. So this is the headline list of causes and appearances of uncertainty in carbon footprinting. So we have here the contextual uncertainties, definitions of carbon footprint. These actually can differ a lot. Logistic system boundaries, how many clients do we take, how many days do we take trips or tours. In the model structure, the allocation method is important, as I gave the example about co-loading of shipments into the same vehicle or of clients into the same trip and same tour. What kind of functional forms we use, linear or non-linear, to express functions of emissions over distance or energy consumption over distance, and also activity assumptions, what type of trips we're talking about, what type of trip generation, and so on. Different variables matter. The fuel used, is it known, is it unknown? What kind of fuels do we distinguish anyway? The trip characteristics, do we know the origin, destination, distance, and so on? So structural variables here, vehicle characteristics of size and weight, and so on. And of course, the parameters for emission factors, for conversions from shipment to payload to vehicle, etc. Many ways we can find where we need additional data that cannot be directly observed, or where we have to estimate across different activities and companies. So our student made a mapping of these uncertainties according to their impact or severity and the difficulty to be resolved. So on the y-axis, you see the impact of different uncertainties that they could have on the uncertainty in the final footprinting and the final footprint indicator. And on the x-axis, you see the difficulty to resolve them. Now, we see three distinct groups here. It's interesting. It's a pattern that emerges once you start to plot these uncertainties. There's a group about definitions, which are reasonably easy to resolve, but they have a big impact. There's about trip data, a category which is a bit more difficult to resolve, but even higher impact. And then there's a category which is quite complicated to resolve, which is about model generalizability, what kind of parameters do we use, and so on, with varying degrees of impact. So we could think we take the ones that have the highest impact here and start with those. So this overview helps to compress the long list that you saw earlier, the large amount of issues to handle when taking a systematic approach. And it could be considered as the headlines of a program for uncertainty reduction. So definitions, trip data, and model generalizability. Now, our next step was to quantitatively assess the uncertainty in a couple of concrete cases. The main question here was how these uncertainties would propagate into a final uncertainty of footprint indicators. This slide illustrates the case study. It revolved around two series of shipments of a transport company working in a construction logistics context. Data were available directly from the company. The type of uncertainties addressed here involved randomness of activities due to variations in trip length, as well as fuel consumption. Empirical distributions, you see an illustration bottom left, were derived here from data or assumed after consultation with experts. Of course, the shape of distributions emerges if you have all the data, but if you don't, you have to assume something like a triangular shape or uniform shape or normal distribution. And some of these uncertainties were simply too difficult to portray with distributions, and they were tackled by scenarios. Together, these created distributions of carbon emissions for a best and a worst case scenario, which you find on the bottom right. As you can see, the eventual variations between highest and lowest emissions exceed a factor of 3, from 10 kilograms CO2 equivalent to 35. It's quite big, quite dramatic. But on the other hand, the quartiles, first quartiles, were found to lie below 20% of the means, so which means pretty focused distribution and slightly skewed to higher levels. In any case, it confirms that uncertainties can create significant variation in final indicators, which is relevant for policy and private industry also. So finally, I'd like to place a call for action, as these findings, of course, they imply a need for improvement of practices. Sometimes these distributions will not matter much, but sometimes the variation, the possibility to vary with these will lend it to manipulation, which is problematic. So within our current scope of measurements of impacts of road freight, there's clearly a need for improved tools and guidelines. The graphic on the right shows one of the ingredients we think is necessary to distinguish between different types of analysis to quantify effects and footprints. Some will be satisfied with scenario analysis, some with uncertainty analysis, and some with a rough or local or global sensitivity analysis, depending on the type of impact it has. Now, it is questionable here whether any additional regulation is feasible, perhaps desirable even. We have a lot of regulation, and these standards are already seen as a burden. But placing all our trust in data accuracy and availability of data appears to be risky as well. So what to do here is still unclear. Further discussions between stakeholders could be important to find ways forward. Now, it is clear that new standards will bring new complications, and the ISO standard, new ISO standard, to account emissions per year might have a dampening effect on these variations, but we haven't studied this, and we think this should be studied further. Now, extending our scope beyond the study, we also see potential impacts for carrier selection. If the environmental criteria become part of the carrier selection process, this could have an impact, and these uncertainties would blur or confound somehow the story, emphasizing also the direct financial implications of uncertainty. We could see modern data storage systems, as addressed in the earlier keynote of the conference, which could contribute to an improved accuracy. Finally, with the new counter-emissions approach being prepared by the European Commission, we also feel it's urgent to extend this whole narrative to multiple modes of transport. This should allow some uniformity between modes, which is relevant for many policy areas, including modal shift, external cost, and financial regulation of the freight sector. I will summarize our main results here. The full report can be downloaded from the TU Delft Educational Repository for details. So, main points. Uncertainty is not negligible. The impact is first financial and second on emissions. We think this is important. And if a variation of a factor of 2 or 3 is possible, then we should try to do something about it. Fundamental sources of uncertainty are definitions, data quality, and model generalizability. These could be the headlines for an improvement program. So, as I said, this factor 2 or 3 makes this whole system prone to manipulation, which creates some urgency. And managing this is not really trivial, given the whole complexity of the story. Underlying, we think that there should be also incentives for uncertainty reduction to make sure that this uncertainty is not exploited. Thank you for your attention.